In this question, we've got a volume that is being of for x squared to the x-axis, and the curve's rotated about between 0 and 3. So this area is rotated around, and we're going to get this little trumpet shape happening in there. So it'll look like that. Again, we're not going to be able to do that using a nice formula. Not like the previous question. So what we've got to do is we've got to use integration. Again, we're going to the idea that we're going to have pi integral of pi y squared dx, because we're rotating around the x-axis there. We're going around this way, so it's going to be pi. It's going to be with respect to x, so it's going to be pi y squared. So we look at y being equal to x squared, so y squared would equal x to the power of 4. So that's where that's going to get x to the power of 4 there, between 0 and 3. We can take pi out all the time. It's just a constant. It will make no difference to our integration because we're integrating with respect to x. So x to the power of 4, add 1 to the power and divide by the power. This gives us x power 5 over 5. We substitute 3 in, we substitute 0 in, that's going to give us 0. Leaves us as 243 pi over 5. Leave that fraction in whatever way you like. I've left it as an improper fraction, but it doesn't really matter what way you've left it. So in question 3, this time the area between -1 and 3 is rotated around the axis. So this one's a little bit different in that we're going on the other side, but that's okay. We're still seeing that same shape. We'd get that area being rotated around. So y is equal to x squared plus 2, so y squared would equal the x squared plus 2 all squared. Now when we're going from -1 to 3, again when pi comes out, we can't integrate this with our rule. It's because it's x squared. Best we can do is expand it. So x power of 4 plus 4x plus 4, then integrate every separate term. Do our substitution in of 3 and -1. Calculate it, being really careful because of the signs to give us that required area. In question 4 here, we've got y is equal to x cubed is rotated around the axis between 0 and 2. So x cubed all squared, we multiply the powers, it gives us 6. So add 1 to the power and divide by the power, substitute 2 in, substitute 0 in, and gives us our answer. Y equals 4x minus 1. This one's not too bad because it's going to be just a straight line between -2 and 3. So -2 to 3 would actually be this area over here. So you actually get a shape that looks a bit like that because that's been rotated there and that part's been rotated there. So -2 to 3, we do the substitution. No, sorry, do the integration first, then our substitution. So this one we can use our rule here because it's 4x, it's a linear function in there, and then do our substitution to get our answer. Question 6, this one's an interesting one that we want to find the volume when the curve x squared plus y squared equals 1 is rotated around the axis. We can do it this way. We can look at it, we can see that with 0 to half, because that's our limit, so that part there is rotated around. We can put y in terms of x there. Now we can do this way, but I'd really probably prefer just to say, look, if y squared is equal to 1 minus x squared, and we're doing pi y squared, so it's going to be integral of pi y squared dx, we've already got y squared. So what we need to do is just go straight down to this line. Prefer probably not to do it that way, just saying because we've seen people go try and get the square root and then square it again, taking up time and effort that they don't really need to do, but also then get it wrong. So you've already got a function in y squared, substitute that in. Y squared is 1 minus x squared, and just integrate it and do as we've done before. So just be wary of something like that. Find the volume of the solid when y is equal to square root of x plus 3. Now this looks a little bit nasty when we start to deal with it, but when we consider we're doing y squared dx, the square root of x plus 3 is going to be squared, so it just becomes x plus 3. We're between 1 and 6, so we can substitute that in. So sometimes we see some questions that may look a little bit nasty when we look in the problem, but when we go to square it, well, that works out to be really nice. So try to be really careful with it. Again, like we've done before, draw up a quick diagram. It won't hurt. Understand exactly where everything is. Be really careful with all the signs that you've got to deal with, and be careful when making sure you get the correct function to integrate.